Okay, so I'm going to pick up from Friday. I believe the only thing I didn't finish last Friday was one last example and then a whole bunch of diploma questions. So why don't I try this one last example here, the diploma questions, then we'll do our last topic. Sound good? So here's kind of a strange problem. Some people wouldn't think this can be solved using combinatorics. Because basically here's the idea. You want to travel from A to B. Let me give you some examples of how you could do this. You could go all the way over, all the way down. That is one route you could take to go from A to B. Does that make sense? Let me show you another route you could take. You could go all the way down, all the way over. That would also work. Now, there's a million different routes. Well, not a million, but there's a ton of different routes you could go. You could go like down, over for a little while, down, over for a little while, and there. So the question is, well, how many different ways could you travel? And if you're looking for a real-world application, anyone who has to design a city or town and has to account for traffic, this would be a good example, where it's like, how do I get from Max to my house? Well, I could take the highway and then this road, or I could go through the back road, and you get what I'm saying here? Right. So anyways, here's how you can solve this using combinatorics. At the end of the day, all of the ways that I've drawn this, though, really what you have to do is you have to go to the right 4 times, and you have to go down 3 times. I guarantee you that happens in every single one of these paths. Let me just count them out here. In the red path, I went right, 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 down, down, down. 4 rights, 3 downs. Make sense? But I did the exact same thing, just in a slightly different order in the other paths. Here I went down, 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 right, 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 right. I still had 4 of one, 3 of the other. Even if you zigzag, there's 1 down, a second down, and 3 downs. And then there's 1, 2, 3, 4 rights. Does that make sense? So I guarantee you, no matter which way you go, you're definitely doing this. Well, in a way, what you then have is 7 letters. You have 7 characters. You have 4 rights and 3 downs. Well, we've already accounted this in a formula for. To arrange those 7 letters, that's 7 factorial. Except we had a special rule. What happens when you have repeated letters? You divide by however many times you repeat them. So since there's 4 rights and 3 downs, whatever this is, that's your answer. It's kind of like the example on like how to arrange letters in the word Mississippi. There were 11 letters in Mississippi, but then there's 4 I's and 4 S's, and you divide by that. In this example here, you're going to travel 7 blocks, but the 4 rights and the 3 downs, really doesn't matter which order you put those ones in. So this is a good way of solving the question. Okay. Anyone get an answer for what it was equal to? Okay. I think it's fair to say, was it 1,260?
I did not get that either.
Okay, never mind.
I got 35.
Yeah, that's what I got. Ew.
Let's try this. You got to go 7 factorial.
35.
Come on, Darian.
And then you got to divide by, in brackets. Don't forget, by the way, if you're doing this in one step, put it in brackets. 4 factorial times 3. Okay, it's 35. You didn't get this right here, guys? You're good? Okay. Okay, let's try some of these diploma examples here. 35. Is everybody good? Okay, so these are off old diplomas. Let's give them a try. You'll discover that most of the issue here is just about, can you understand the context of the question? And then how can we use the rules that we've learned to solve? For the most part, there's no work. So here's the first example. You want to go park in front of the local 7-Eleven. I don't know, whatever, right? There are 6 parking stalls, and there are going to be 5 cars to take those parking stalls. How many ways can this occur? Well, here's the fast answer. There are 6 stalls. Let's pick 5 of them to be used. That's the answer. Another way of looking at it is that's the whole point. This is all about little tricks. So, oh yeah, we learned this. Here's another way of approaching it. You're the first person to come in. How many parking stalls do you have to choose from? 6. Okay, 6. Let's say you chose this one. This one's now full. The next person that comes in, how many parking stalls are left? 5. Okay, so this one's now filled in. Now how many are left? 4. Then how many are left? 3. Then how many are left? 2. By the way, if the last person needs to come park, does he have a choice? Yes. One choice. Yeah. We're talking about that? So, was this 720 or 120?
Oh yeah.
Let's try another one here.
Why are you not in posting?
Yeah, they're both actually 6 factorial, yeah. Yeah.
Is this the number of, if there's 6 cars and there's 5 cars?
Yeah.
Then if the last person is the 5th car.
Well, because this is the first car with 6 choices. Second car, third car, fourth car, fifth car. So now all 5 cars have parked. Does that make sense? Because the question here was the number of ways that 5 different cars can park. So here are all 5 cars that are parked. That 6th person, like the 5th person, has 2 choices left, right?
Oh.
But that's not what it asked. It didn't ask how many choices the 5th person has. It has how many different ways can those 5 cars park, though.
Oh. So like the last one's just hypothetical kind of?
Yeah, so like if it asked you hypothetically how many different spots could that 5th person park in, that's a different question than how many ways can the 5 cars be arranged. Okay, here's another example. We've got 5 different types of vegetables going into the supermarket, and the question is, how do we arrange them with the stipulation? Is everybody paying attention? Thank you. How do you arrange them with the stipulation that the pumpkins and watermelons cannot be together? Yeah. So, for my silly example, if you're here on Friday, this is the example of, they loved each other so much we treated them as one person, but now they've broken up. How do we solve that problem? Who remembers? Okay, Abby, you're close. Find the ways in which they are beside each other and subtract, and that involves timesing by 2, but then subtract that from the total number of ways. So, let me try this one with you. Imagine there were no restrictions. If there are 5 items, how many ways can you arrange the 5 items? 5 factorial. That is the total number of ways. Some of those will involve them being next to each other, some of them won't. Now, if we subtract the ones in which they are next to each other, then what we'd be left with is the ones in which they are not. So Darian was kind of on the key there. You do have to times by 2 to find when they are next to each other, but what else changes? It's not 5 factorial. Yeah, it's 4 factorial times 2. Because what you do is you treat the 2 items as though they are one person. Why do you have to double it? Why the times 2? Yeah, because it could go AB or it could go BA. So 5 factorial, I think, is 120. I don't know what 4 factorial times 2 is in my head, though. 72, you said?
Sorry. 72 is the final one.
Oh, okay.
Sorry.
So 48. So 120 ways total minus 48 ways in which they are leaves 72 in which they're not. Thanks, Darren.
Wow.
Any questions on that one? Okay, next one. You are being given a survey of all the different activities that you might like to do. Basically, it's simple. You just either put an X in it if you like to do the survey or leave it blank if you don't want to do it. The question is, how many ways could you fill out the survey? So let me give you an example. I could say that I like doing canoeing and bowling. That's one way of filling it out. I could say I love everything. That's also possible. There is also the possibility that when you fill out the survey that you do nothing. I hate going outside. And I don't even like video games. So here's the question. How many ways could you fill out the survey? Let me give you some possible ways of solving this. You could go 7, pick 7. You could go 7 factorial. You could go 7 squared, or 2 to the 7. One of those is the right answer. 2 to the 7 is right.
What?
2 to the 7 is the right answer. Good job, Abby. Yeah. This is like the Subway problem. This is, do you want lettuce, yes or no? Do you want ketchup, yes or no? Do you want canoeing, yes or no? Can you guys see why this could be super duper frustrating?
Yes.
How much work was there to that? Yeah, none. Yeah. Which is why you might hate the first time you write one of these quizzes. If you need to do pick, you gotta go type in a number, math, over to PRB for probability, NPR, and then whatever you're picking. We're gonna do that today, actually. Okay, next example here. 12 people in line, but Stephen, Crystal, and Jason. Shh. Except my grade 9s. You guys are better than this. Okay, Stephen, Crystal, and Jason have to stand together. Twist. This is not a group of 2 that has to stay together. It's a group of 3 that stays together. Crystal and Stephen love each other so much they got to be with each other, and Jason's the third wheel, who's always there too. Well, not you. Anyways. So, can we take what we've learned and try to figure out how to extrapolate this to a 3-person group that has to stay together? Any thoughts? There were 12 people.
Now there's 10.
Okay, so we're going to treat the group of 3 as one big collective, so we need a 10 factorial. Well, there is a 10 factorial here. Now, you know how we had to times by 2 in the last one?
Times by 6.
Well, it's actually times by 3 factorial, which is 6.
Yes.
Why 6, though? How did you figure out 6, Darren?
Because like Jason could be in the front or the back or the middle.
Yeah.
And then it gives like 6.
So you can go Jason, Crystal, Steven. You could go Jason, Steven, Crystal. You could go Steven, Jason, Crystal. Steven, Crystal, Jason. What have I missed? Crystal, Jason, Steven, Crystal, Steven, Jason. Well, you know what that really was? All of the ways to rearrange the group of 3 was 3 factorial, because there were 3 people who could go first in this little subgroup, then 2 who could go next, then 1 who could go next. So the final answer to this one was actually B. I know there were 12 people, but really one of those is really a group of 3. So there's not 12, there's actually 10 items. One of the items is a group of 3, and inside that group of 3 you can do some rearranging.
Okay.
Okay. Here, if that didn't make sense, let me do an items thing here to help out with that. Because that was a tricky one. Okay. So here is my here's a whole bunch of items. You guys can see them here. Let's make the group of 3 here be these 3 guys because they're the non-pens one, okay? So rather than having 12 items though, why don't I go with 1, 2, 3, 4, 5, 6, 7, 8. Okay? So first thing we're going to do is rather than having 8 items, we're going to treat these guys all as one big group. Fair enough? So I have 2 less items. I used to have 1, 2, 3, 4, 5, 6, 7, 8 items. Now I have 1, 2, 3, 4, 5, 6 items. So that's why we've gone down by 2. Now, this group of people can get rearranged, but only if I graph them as a whole group. Okay? But now, ignore the rest of these guys for a second here. As this group, when there were 2 of them, there's only 2 ways of doing it. It can either go this way or this way. But when there's 3 of them, it can go this way, this way, this way, this way, this way, and I've missed one of them, right? So as the group of 3, it's really best to say, well, there's 3 choices for who can go first, 2 choices who can go second, 1 choice for who goes last. That was 3 factorial. But that 3 factorial was inside of a larger 10 factorial. Make sense? Again, how much work is there to it though? None. And that's what kids find frustrating here, is that in my experience, in order to get good at this section here, you just need to try a lot of questions. And the more you see, the more you go, oh, I had one of those before. Okay. Everybody have these notes ready? This is kind of the last set of notes in a section, okay? I usually try to teach these three all in one big grouping here. And then after this, I've hopefully given you all of the tricks and twists that I can kind of think of for now. So I want to present, again, kind of a basic scenario here. And this works well when it's ever around zones or provincials time, because I think kids who do basketball or rugby, they get this concept. Here's the first one. You've got 8 teams at the basketball tournament, and the question is, how many ways can you award medals for the top 3 teams? So there's a gold medal, a silver medal, and a bronze. What do you got? You're trying to sing it out loud. Say it out loud. Not 8 pick 5, 8 pick 3. Because there's 8 people and we're going to pick 3 of them to win. Let me show you another way of doing that. For gold, you had 8 people who could win gold. And then for silver, there's 7 who can win silver. And then for bronze, there's 6 who can win bronze. What about everybody else? Yeah, nothing. Here's another way of approaching this. You could have called this 8 factorial over 5 factorial. Okay, that'll work too. And here's another way of thinking about it. You could have written this 8 factorial over 1 factorial, 1 factorial, 1 factorial, 5 factorial, which is dumb, but let me explain why. There are 8 people playing in the tournament. 1 person gets gold. 1 person gets silver. 1 person gets bronze. And 5 people get thanks for trying. And it doesn't really matter whether you're 4th through 8th, you don't get a prize. Does that make sense? Any of these ways of solving things get you the same answer. But I want to take that, which we've already learned here, and add one little twist on it. You have a tournament again, but the top 3 teams get to go to provincials. Now, some kids would argue, well, it's better to be the first seed than the second seed. But if I just tell you, look, we're having cuts. Even if you're the 3rd team, you still get to go. Does it really matter then whether you're first, second, or 3rd? The answer is no. Sometimes there's a scenario where it doesn't really matter whether you make it 1st or 2nd or 3rd. All that matters is that you make it. Does that make sense? You could be the first choice, you could be the last choice, but all we care about is that you actually were chosen. Does that make sense? Well, this changes things a little bit. Rather than there being 8 teams and having 1 first place team, 1 second place, and 1 third place team, really, guys, please listen. Even just for my sake, you're distracting me. What you really have is a 2-part split, where either you make it or you don't make it. Does that make sense? There's not first, second, third, and everybody else. There is the people who get to go and the people who do not get to go. The denominator of this fraction always has to add up to the numerator. Does that make sense? Whatever the bottom is, in theory, needs to add up to the top. There are 3 people who get to go, who are like, let's call them winners. And then there are 5 who let's call them losers. Sorry, someone has to lose. Let me give you a different scenario here. I am going to pass out some prizes, hypothetically in class. Okay, here's the prizes. I'm going to give out $5 to 3 different people. Now, let's say I hand out $5 to Darian first, and then $5 to Cassidy next. Let's say that Jason gets my last $5. Does it matter to Jason that he was the last one to get $5? Why not? Because he's still a part of the group of people who got $5. Change the scenario slightly here. Let's say that I pass out $1 million to the person in first, $10 to the person in second, and a handshake to the person in third. Now does Jason care that he was third? Yeah. So there are some scenarios in life where it really, really matters whether you're first, second, or third. And there's some scenarios in life where it really doesn't matter so long as you get the same prize. Have I made that kind of idea clear? The struggle then is it a scenario where it's 8 over 1, 1, 1, and 5? Because each of these people got an individual prize? Or is it 8 over 3 and 5, where all of the winners got the same prize? That's what we have to distinguish between, because it makes a huge difference. Here's the notation we use. I like to call it a choose. When it's P, I call it pick. When it's C, I call it choose. But really the official words are permutation and combination. Essentially the way it works is that a permutation, it really matters whether you're first, second, or third. In a combination, it actually doesn't matter who's first, second, or third. Which then leads to the ironic part of a combination lock. You guys have combination locks? Does it matter what order you put your combination in?
Yes.
Actually, it does, which is silly because you don't actually have a combination lock. You actually have a permutation lock. Because if you had the locker com, like say 10, 20, 30, if you were to type in the code 20, 10, 30, that wouldn't open your locker. So the basic concept here is in a combination lock, the order is not important. If your first, second, or third get flipped around, it's still the same thing. So here's my examples. If you were to type in all of the right digits for your friend's phone number, but you have them in the wrong order, it wouldn't work, right? But if all we care about is the top 2 teams go to zones, then it really doesn't matter. So, anyways, here's the notation. You'll either see NCR, you might see N over R in brackets. Can I point this out, guys? I know I have test questions on this. Just want to make sure I point it out. If you ever see N over R in brackets, like say 17 over 2 in brackets, what this really means is 17 people choose 2 of them. Another way of writing it is to say there's 17 people, 2 of them get to go on, 15 of them lose. I love sports analogies. Imagine that you're trying out for a team. This team, only 2 make it. Really, really exclusive team. I don't know what the team is. Badminton doubles. Okay, 17 people trying out for the best team in our school. 2 make it to badminton doubles. It doesn't matter whether you're the first person or the second person picked. 2 make it, 15 don't. If I want to go back a slide here, this notation right here is 8 choose 3. This was 8 pick 3 because each of these 3 was unique. This is 8 choose 3 because who cares? Have I made that point okay so far? Your biggest struggle then is to figure out which scenario it is. So let's try some more examples here. This was a picture I used to try to illustrate the idea of, let's say that I wanted you to have 2 cards. If you were to start with, say, like a heart first and then a diamond, if order doesn't really matter, then later on when you have a diamond, then a heart, I cross this one out because we've already accounted for that possibility. Does that make sense? Like, if order truly doesn't matter, if you go heart then diamond, well then over here we shouldn't count diamond heart because we already counted that one earlier. One thing I need you to know is that choose is always less than pick. Watch this. If I do 17 and I choose 5, not random 5, that's not. Oh, come on. So I can choose 17, choose 5, and then if I do 17, pick 5, choose is always considerably smaller. And the reason why is that when you're doing a choose scenario, you're getting rid of some of the outcomes that have already been accounted for. Since we've already accounted for spade heart, then when I do, well, right here, heart and spade has already been accounted for. So let's not count this one a second time. That's basically what's happening when you do a choose one. Okay, let's try some basic examples. 5 kids out of 10 get to go on a school trip. Imagine here's the scenario. There's 10 of you here. You get to go. 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 Doesn't matter what order I pointed at you in. Okay, so because of that, it is 10 choose 5. Another way of thinking about this is that there were 10 people. 5 ended up in the group who get to go, and 5 ended up in the group who don't get to go. This is the same thing, by the way. So whatever that number is. On this one right here, 15 employees. 3 get to go do a presentation. 12 get left behind. There's actually two ways I could write this. This could be 15 people. I'm going to choose 3 to go. I want to show you something really weird. You could also have it as 15, choose 12. Try it in your calculators. Type in 15, choose 3, and then type in 15, choose 12. You're going to discover it's the exact same number. Here's one of the reasons why you can kind of change your perspective. If I told you that there were 15 people and 3 of you got to go give a presentation, who would be like, yay, I want the presentation? Well, maybe someone does, right? And so maybe they're like, yay, I made the presentation team, right? But you could also approach it the other way and say, well, of the 15 people, 12 of you don't have to go give a presentation. Maybe you're like, oh, please let me be one of the 12, right? Like, you can actually approach this either from the 3 or the 12's perspective, right? And so if you wrote it, 3 get to go and 12 don't get to go, it's the same thing as saying 12 don't have to, 3 do have to. So one of the interesting things about combinations is that I can predict that, say, like 10 choose 4, it's going to be the exact same thing as 10 choose 6. Does that logic make sense? Because this really means 10, 4 go, 6 don't. This means 10, 6 don't go, 4 do go. It's actually the same thing. Okay, just to make sure I'm being really thorough here, because these are really basic examples, I want to hop ahead to my my diploma examples when I can. This one right here, 3 swimmers get selected for the school team. Does order matter?
No.
5 choose 3. 5 swimmers, but now we give out gold, silver, and bronze. 5 pick 3. Do you guys feel like you get the difference here? Yeah, whether order matters or it doesn't. You grab the door for him. Here, why don't we go do some of those diploma questions, and then I'll come back and do what I skipped. I think you guys are ready to try these ones now. So now that I've shown you guys a little bit of stuff, let's walk through. Let's do them as a group. You guys can look them over and try to beat me to the answer. But so find the soccer one first. This is off an old diploma. There's 12 teams in a soccer league. Each team has to play each other twice. The question is, how many games will there be? Now, clearly, as you guys look at the 4 answers, it either involves pick or choose. And as you look at some of the answers, some of them are 12 choose 2, some of them are 12 pick 2, some of them get doubled. The question is, can we try to figure out the logic as to how to solve it? So, again, imagine the scenario here. Imagine we're in the gym and 2 people are going to play each other in a badminton game. There's 12 of you. Let's say that I pick you to go play and I pick you to go play. Did it matter which order I pointed at you guys in? Because at the end of the day, what's happening is of the 12 teams, 2 of them are playing and 10 of them are not. Should it be the pick or the choose then? Choose. Okay. Well, then the answer is D, because everyone has to play each other twice. See how that works? So order doesn't matter. Because really, whether Vancouver plays Calgary or Calgary plays Vancouver, it doesn't matter. They're playing each other, right? Okay. On this one here, what we've got is we're going to make a committee. The committee has to have 5 guys and 4 girls. And I'm going to tell you what the pool of selected people was. There's 10 men. We need 4 of them. There are 13 women. We need 5 of them. Now, as you guys look at some of the possible answers, they did 10 with 4, 13 with 5, here and here, and 1 was choose, 1 was pick. Other possibilities, if you take 10 and 4 and add them together, that's, if you do 10 and 13 together is 23, and this is 9. So then the other way is, well, what if you need 9 out of 23? I want to take a stab. Which one do you think is the right answer? The answer is A. Good job. Yeah, the rationale is there are 10 guys, you need to choose 4 of them, and you need to have 13 women, and you need 5 of them. what would it take for it to be this answer right here, C? What would it take for that to occur? Yeah, if it basically said, here's the selected pool, but like this one right here means you could have all men or all women. Right? Because you have to have some men on the team and you have to have some women on the team. Hence multiply. And you need to have men and women on your team, though. That makes sense? If it was a plus in between, you could have a men committee or you could have a woman committee. But because you have to have men and women on your committee, when both have to happen, you multiply. Does that make sense? I still lost you, eh? Okay, so let's say you're making your committee. Randomly, you decide, let's pick the guys first. Okay. So there are 10 guys. You need 4 of them to make the team, 6 of them not to make the team. Essentially, that's 10 choose 4. Okay. Pause for a second. Then consider the women, which you could have done the girls first, but who cares who you did first, right? For the women, there are 13 of them. You need 5 of them to make the team and 8 not to, which is 13 choose 5. Well, you need 4 men and you need 5 women. So whenever you have an and, you multiply things. But if it was, say, the sort of committee where it was either you had 4 men on the committee or you had 5 women on the committee and you had just pure guys or girls on the committee but not a mixture of them, that would be an and. That would be adding. But because of this word right here, it means to multiply. That answered your question. Okay. Okay, this is something that if you're in Dash 1, you should prep for. Dash 2, I'd like you to be ready, but I don't think it's as likely. But in Dash 1, definitely. What they could do is they could ask you to follow somebody's algebraic work. Okay. Yeah. So on this one right here, one of the things you may be asked to do is take n choose 2 equals a number and solve for n. So like what they're telling you is n choose 2 equals 10. The question is, well, what is n? And this is actually a really challenging task because it's not like you can just divide both sides by 2. It doesn't work that way. I'll show you where the mistake was. It was actually in step 1. And the reason why is, what does something choose 2 mean? Well, it means that you need the n factorial on the top, and then on the bottom you need the 2 numbers. One of them is 2 factorial, and then the other one is whatever is left over. It would be n minus 2 factorial. Like if this was 20, it would be 20 over 2 and 18. But look at their work right here. Did they actually make the formula properly here? No. If I could, I'd like to actually show you how to solve it properly then. Then what you'd do is you'd times by, you actually need an extra 2 factorial here. What you could then do is take this 2 factorial and you could multiply just the 2 up to their side, giving you n factorial over n minus 2 factorial equals 20. Because this 2 right here, I'm going to bring up there. Well, not 20 factorial, it's 10 times 2 factorial. What's 2 factorial though? 2, because it's 2 times 1. Right? This is a really good point here. 20 times 2 factorial is not 40 factorial. Because only this guy gets factorial. So, anyways, what ends up happening here then is that this means n minus 1, n minus 2, n minus 3. This guy means n minus 3, and like you can cancel all this stuff, and it eventually gives you a quadratic. You can actually solve this, if you can follow my mess here, to n minus 1 equals 20. But I think I need to do that better because I'm really messy here. Let me erase that and do a better job here. This was supposed to be n over n minus 2 factorial, and it was supposed to equal to 20. Is everybody okay with me after that step there? I lost you at that step? If I start here, is that an okay starting spot? Okay. N factorial really means take n times by 1 number less, times by 2 numbers less, times by 3 numbers left, and just keep doing that. n minus 2 factorial means start with n minus 2, go lower than that, and just keep going. What we've learned previously is that a whole bunch, no, not that one, a whole bunch of these things should eventually cancel. And what I'm left with is n minus 1 equals 20. This is actually quadratic, and you can use quadratic formulas to solve it. I'm not going to solve the rest of it. I just got to point one thing out. When you get a quadratic, you usually get two answers, right? It could be that there actually are two answers that work. There's another possibility. You might get an extraneous answer. Let's say that n is a negative number or a fraction number. It wouldn't work because we've learned already, guys in the back, we've learned already that the only numbers that work are positive whole numbers. I can't have negative 5 and choose 3. I can't have 4 and a half and choose 7. Does that make sense? So you could keep solving this and then you'd get what n happens to be. Okay, let's move on. This is another one that's mostly geared at my dash 1s. But if you're in dash 2, you probably should watch anyways, because it could happen. What I'm going to tell you here is that n pick r is 6720, but I don't tell you either n or r. And then later I tell you that n choose r is 56, but again, you still don't know n and r. The way to solve this then is to know how the formulas work. This means n factorial over n minus r factorial is 6720. This formula right here means n factorial over n minus r factorial, and then the extra r factorial is 56. I'm literally using the definitions of where these formulas came from to help me get started. And now I'm going to go stand up at the board to help point something out. From this one here to this one here, what is the only difference between the two? Okay, look at this number right here. This number right here is much bigger than this one here. I already tried to point this out today. Why is this always got to be bigger than that? Because this divides by more stuff. I don't know what these numbers here are. And I don't know what these numbers right here are. I'm in the woods on those. I'm lost. But what I do know is that this number here is bigger because it doesn't have to divide by an extra r factorial. This number here is smaller because it does have to divide by an r factorial. So here's how you solve this then. What you'd really say is that if I were to take 6720 and if I were to divide it by r factorial, wouldn't you get 56? You follow that logic? This number right here, the only reason why this number is so big is because it wasn't divided by this extra r factorial. So if I were to take this number here and divide by the r factorial, then I would get 56. Well, now here's how you'd solve it. I would rearrange it and do this. And then this is where there's actually mathematical operations fail us. If I take 6720 and I divide by 56, I get 120. Here's the problem though. There is no button on your calculator, that I know of at least, to undo a factorial. So you just have to kind of just guess and check. So I'd start with like say 4 factorial. Nope. 5 factorial. Ah, there we go. Since 5 factorial is what gives us 120, then r must have been 5. Okay, here's the good news though. Should you bother trying negative 7 or 2.2? It has to be a positive whole number. So. I'm doubtful that'll show up on a dash 2 test, but it could. Like in theory, it is part of your outcomes, but the difficulty level is a little bit higher there. So if you ever get a question like this, take this number and this number. When you divide them by each other, the difference must be whatever this little extra guy here is that you divide by. Okay. Another one that's kind of similar in terms of its concept, because this one throws kids off because they look at the question and they only see one number. Close that window, I think it's. There's only the number 91 there. Here's the scenario. You've got a certain number of people at a meeting, and when they're done, everybody's going to shake hands. Somebody decided to take track of how many hands got shook. I don't know who keeps track of this, but somebody did. When they were done, there were 91 handshakes. A lot of kids on this one, they wonder, how do I even get started? It's actually this. An unknown number of people are going to choose to shake hands. How many people do you need in order to shake hands? 2. Yeah. 2 at a time, people are going to shake hands. And when you're done, it's going to equal 91. So one more time. An unknown number of people are going to shake hands in groups of 2. Now, does it matter whether I shake hands with Darian or Darian shakes hands with me? Does the order in which we shake hands matter? That's why it's choose. So then here's the question, can you solve for n? I'm going to show you guys the algebraic way of doing it, and then we're never going to do that because there's a faster way. But you could do this. You could go n factorial over n minus 2 factorial 2 factorial. That's what n choose 2 means. I don't know what this number is right here. One of the bottom numbers is 2. The other number is what's ever left over. That equals 91. This is what I was trying to show you on the previous slide. Anyone remember what to do next? Yeah, times the 2 up, because this is really 2. So times the 2 up and make this 182. And then n factorial is really n minus 1, n minus 2, etc. The n minus 2's can cancel, and what you're left with is n minus 1 equals 182, and you can use quadratics to solve it. That being said, I hear a couple of you guys already know the faster way of doing it. Just guess and check. Yeah. So take 14 and choose 2, see whether it's 91. Take 15 and choose 2, see whether it's 91. Take 24, you know what I'm saying here? Has anybody tried the guess and check yet? You guys must have. Which one was it? 14? Okay. So the handshake question, by the way, is a really common question type. It throws kids off because they only see this number right here, and they wonder, well, what's the other number? But when you shake a hand, it implies that you need 2 people. And sometimes that's kind of hidden. Is that the last one?
Yes.
Okay. Let me just look back through the examples that I skipped, see whether any of them are really important to do. Okay, how about this? Can I do this slide here, and then the one in front of it, and we'll call it a day? I want to do this one here first.
So the order matters.
Okay, what I've got here is 4 different questions that should hopefully be solvable just in like one step. We just have to know what the scenario is asking here. Let's say that you're getting pizza. There's 25 toppings available for pizza, and you're going to get 4 of them. Let me give you some possibilities. You could do this. 25 to the 4, 4 to the 25, 25 times 4, 25 pick 4, or 25 choose 4. One of those was the right answer. 25 choose 4 is right, yeah. Because there's 25 toppings, and does it matter what order they go on? No, because if you have ham and pineapple, or you have pineapple and ham, don't you have the same things on your sandwich, on the pizza by the time you're done? Oh wait, for this one right here, we've got 6 people standing in a row. I can't even think of good distractors. The answer is 6 factorial. You could also, by the way, have gone 6 people, and let's pick all 6 of them to be there. That could also work. Okay, blackjack. Zinte. Do you guys know how blackjack works at all? How many cards are in a blackjack, or in a deck of cards? Do you guys know? Yeah. And how many cards do you need when you play blackjack? Do you guys know?
2.
You need 2. The answer is 52. Choose 2, because it really doesn't matter whether you first have the ace then the king, or you have the king then the ace. By the time you're done, you have an ace and a king. This last one here is a bit different. You might need to answer it like this. There are 10 trees, but the 3 pine trees are indistinguishable from the 4 elm trees, which are indistinguishable from the 2 birch trees and the 1 willow tree. Now, why can't I do 10 pick something or 10 choose something? pick and choose really only work if like there's only one grouping, or like you can split them into two groups. But because I've got four different trees going on here, I've got pine and elm and birch and willow, I kind of have to do it like the old-fashioned way. But if it was like just birch and willow, there were only two objects, you could do choose or pick perhaps. But as soon as you start having more, like you have these ones and these ones and these ones and this one, you kind of have to revert back to this one. Okay. Yeah, let's finish with this and then we'll call it a day. Where does this get used in everyday life? Gambling. Yeah. If you are a person who likes to gamble, not that I'm advocating it, but math is a huge part of it in terms of knowing odds and probabilities. So what I wanted to walk you guys through is just a basic idea about how to figure out number of permutations for poker. If you guys don't know a lot about poker, don't stress out over this. It's not like I'm testing you on it. But in case you do play poker, this is kind of a cool overlap. There's 52 cards in the deck. If you want them all to be black cards, here's how you figure this out. There's 26 cards in the deck that are black. And when you have a hand in poker, a poker hand has 5 cards. So if I wanted you to have all black cards, 26 cards in the deck are black, you need 5 of them. Does it matter if you get dealt the ace before the 5 before the 3? Well, no, at the end of the day, that's what you have, right? So order doesn't really matter. Well, so this is how many there are. If you wanted to figure out probability, what you'd do is you'd say there's 26 choose 5 ways of selecting only black. And then you'd divide it by 52 choose 5 because that's the total number of ways of doing things. Does that make sense? The answer, by the way, is not 1 and 2 because some kids would be like, oh, look, 26 over 52 is 1 and 2, but that's not how this works, though. Okay, let's talk about a flush. Do you guys know what a flush is in poker? All are the same suit. Okay, so how many cards are there in a suit? Anybody know? 13. And you would need all 5 of them to be the same. However, this isn't it, though, because this would be a flush, say, in diamonds. Or you could get a flush in clubs. Or you could get a flush in spades. Or you could get a flush in hearts. Here's the fastest way of writing this. There are 13 cards in a suit. You need 5 of them. But this could happen in 4 different ways. Does everybody get why I have to times by 4? Because you could have a hearts flush or a diamonds flush. Or, makes sense? So because it can happen multiple ways, we'll times by 4. How does it change then if it has to be a flush in diamonds? Then it's just 13 choose 5 the one time. Yeah. Okay, let's say you wanted to figure out how many ways there is to get 4 aces. How many aces are in the deck?
4.
How many of them do you need? No, you need 4. By the way, 4 choose 4. Not 0. 1. There is one way to have 4 hearts, or 4 aces, and to get all 4 aces. The one way is to have all 4 aces. Yeah, totally. Now, but we're not done, though. We're not done, though. When you have a poker hand, you need 5 cards. You only have 4 cards right now. Now, the other card can be literally anything else in the deck, though. How many cards are left in the deck that are not aces? That are not aces. 48. So there's one more part to this. You need, of the 4 aces, you need all 4. And of the 48 other cards, you need one of them. I don't care which one it is. It could be 4 aces and a 2, 4 aces and a 7, 4 aces and a jack. It doesn't really matter, right, what the other card is. But it's really important to keep in mind that this 4 right here plus this 1 right here mean that you have a 5-card hand still. So as I'm reading this out, there are 4 aces in the deck. You need all 4 of them. And there's 48 other cards out there. I don't care which one of the other 48 you have, but you do need one more card. Last one here. This is a full house. 3 kings and 2 queens. Well, here's how this works. There are 3 kings in the deck. There are 4 kings in the deck. You need 3 of them. And there are 4 queens in the deck. You need 2 of them. See how this 3 right here and this 2 right here still adds up to 5? You still have a 5 card hand. The way that poker basically works then, if you know anything about it, is that the most rare hands don't happen all that often. So like if you were to actually calculate this number, I believe this one is 48. Can anybody do this one for me? 4 choose 3 times 4 choose 2. 16. That sounds like it could be right. You wouldn't need to on this one. 16. 24? I'll look at yours in a second, Jason. Now, if you guys did calculate, like, say, 26 choose 5, though, this number is probably really big, right? So the reason why, like, a straight flush or 4 of a kind is worth more in poker is because it's more rare. Less of them are possible. Does that make sense? It's very easy to get a pair. I know this is not on there, but why don't I finish with this last one here? In order to get a pair, the way it works is that you need 4 cards in a suit. You need 2 of them. So like let's say of all the aces in the deck, you need 2 of them. But this could happen in 13 different types, because you could get it with aces, or you could get 2 3s, or you could get 2 4s, or you could get 2 5s. And then of the remaining 48 cards in the deck, you need 3 of them. If you were to calculate this is very easy to do. There's lots of ways to take 2 cards out of 4 and get those in 13 different types of cards, and then pick 3 other random cards. And take that times by 13. 48 choose 3. You gotta do change answer to 48. Or do this, yeah, do that. 48 choose 3. Right. So Abby, that was what, 13 1 million. Yeah, 49088. This is how many combinations there is to get a pair of cards. You need 2 cards out of 4 in any one of the 13 different types of cards, and you need 3 other random cards from the 48 remaining in the deck. So it's very easy to get a pair, but it's very rare to get 4 aces. That's why 4 aces beats a pair. Does that make sense? Okay, I'll stop because it's basically the end of the day. So here's my hope then, guys. Over the next couple of days, now start working on your assignments. If you feel like you need to ask me for help on every single question, that's okay. While you're getting to learn this, it's tricky, okay? And if the quiz on Thursday doesn't go well, don't worry about it yet, okay? It takes a while to kind of really wrap your head around this. Okay, we'll talk to you guys later.